Hey guys, Chili here. Welcome back to Intermediate C++ Tutorial 20. Today we got a huge topic. We're talking about move semantics and Rvalue references. This is some big stuff that came in with C++ 11 and it revolutionized the language, and it's probably one of my favorite features from C++ 11. Now, before I jump into the main topic here, I want to just give you guys a little bit of a motivation for why move semantics are important and required. So, we've got the sprite code here. I've added to surface here, I've added a bunch of announcement calls here to output debug string. So it's going to announce when things like constructors and destructors and assignment operators are being called. Now, if we go to game.cpp, we're going to be loading a bunch of surfaces into a vector. This is a vector of surfaces. And if we run this, we're going to get something maybe a little interesting in here. We can see here surface loaded from file. That makes sense. But here we're calling the surface destructor a whole bunch of times. And we're calling the copy constructor a whole bunch of times. You can see here, as we're loading files, we're calling copy constructors and destructors. Now, if you've watched my video on vectors, you already know what that means. Let's take a look here. So when we try to construct a new surface in our vector, first thing it's going to do is going to check to see if the capacity can accommodate another surface, and we see that it cannot. So it is going to allocate a new larger block of memory, and then it's going to copy over the objects from the old block. And this copy has to be a deep copy. It's going to call the copy constructor for surface. So copy constructor is going to allocate blocks of memory here. It's going to allocate buffers for the pixels, and then it's going to copy every pixel over here. So it's going to have to do a deep copy of every surface into here, and then it can construct the new surface that we wanted to put in. And then it's going to destroy this block of memory, which is going to call the destructor for these buffers of pixels. And you might look at this and say, well, this is kind of a waste, isn't it? We're making an exact copy of these buffers of pixels, right? Why don't we just make this guy point to the old buffer? We make this guy point to nothing now. So we can basically, because this guy is going to be destroyed anyways, why can't we just steal the buffer from here, put it into new one? We don't have to reallocate this memory. We don't have to copy all the pixels. Wouldn't that be a much better world? And that is what move semantics allows us to do in a very elegant way. Now, in order to understand move semantics, you need to understand what an Rvalue is. What I'm going to do here is I'm going to give you a very simple idea of what it is. I'm not going to give you a technically correct 100% to the specification definition of Rvalues, but I hope you understand what I'm trying to do here. So, what's an Rvalue? Well, Rvalue means values that can only appear on the right-hand side of an assignment operation. So for example, literals, an int literal, cannot appear on the left-hand side, only on the right-hand side. It doesn't make sense to try to assign the value 69 to the literal value 420. Does 420 now mean 69 in perpetuity? It doesn't make any goddamn sense. The other kind of Rvalue that you're often going to run across is temporary return value from a function. So if a function returns by value, that value that it poops out is going to be a temporary. And it doesn't make any sense to assign to a temporary variable, because that temporary is going to die anyways. No matter what you change it to, that guy is going to be dead. So assigning to a temporary doesn't make any sense. You can't do it. So Rvalues, temporaries and literals, are the two main ones you're going to run into. Now, if you might be asking, well, if there's Rvalues, then shouldn't there be L values as well? And yes, there is. L values are values that can appear on the left-hand side of assignment. They are things that you can assign to, that you are allowed to change. So for example, a variable like x here, we can assign number to it, obviously. If let's say I've got a class A, it's got a function get, and it returns a reference to one of its member variables. I can assign to that reference to modify that member variable. So that reference that it returns is an L value type. And again, if you've got like an array, you can index into that array. That's an L value. I can assign to that. Now, this distinction between L value and R value is very important and very useful. Let me show you a simple example here. So what I've got here is I've got a simple function. It is going to take a reference to a string. It is going to mangle it a little bit, and then it's going to output the mangled result. Now, because we don't want to just mangle any string that someone passes to us, they may not want to have their string actually mangled. What we do is we create an internal copy, we mangle that copy, and that is what we output. So we're not going to mess around with the strings that are passed into us. We get the mangled version and the original remains untouched. That makes sense, right? Now let's look at a little different scenario. We're going to call nom nom nom, but we're going to call it with a temporary string. We're just constructing this string here as a temporary. And after this statement finishes, this string is going to be destroyed. So this actually seems kind of wasteful, doesn't it? We are passing in this string into here. It is going to make a copy of it and mangle that copy and output it. But then the original is going to be destroyed. It would be nice if we could just detect, oh shit, this thing is actually just going to die. We don't need to make a copy. We can just mangle the original because it's going to die anyways. And that is where our value references come in. So what we can do is we can overload this function nom nom nom. But we'll give it a different type. So we're going to give it std string, and you put double ampersands here. I'm going to call this one donor because this type is going to donate its resources to us. So this is how you overload a function to take an R value reference. And what the compiler is going to do now is, if it's a temporary like this, it is going to be an R value reference that is going to get dispatched to this function here, not to this one. And in this one, we don't need to make the copy. So here we're going to modify the string in place, donor, and then output that. And we're also going to announce here if we're calling the R value version or the L value version of this function. If we run this, we can see that the first one calls the L value version, the second one calls the R value version. So we can allow the compiler to choose a different version of the function depending on whether the value being passed in is a temporary or not. And the way we do that, the way we indicate that, is with these two ampersands. Double ampersands here doesn't mean logical and, it means this parameter here is our value reference parameter. So we'll only use this function if the thing is an R value. And generally in the R value reference version of an overloaded function, you are going to say, well, this thing here is a temporary. I can do with it whatever I want. I can steal its resources, its buffers, its pointers. I can modify it any way I want. I don't need to make a copy. Whereas in this version here, you're saying, okay, the caller probably doesn't want me to fuck around with its shit. So I'm going to play nice. I'm going to make a copy and only use the copy. Now, let's say we've got some string S. This is an L value, but we don't care. We don't want it anymore. And we want to allow the function to do whatever it wants with it. What we can do is, well, we could convert this to an R value reference just like you would cast anything else. So we can run static cast string R value reference, and what that's going to do, now it's going to call the R value version, and after nomming, it's now going to be all messed up. So you can convert things to R value reference, and that will allow the function to steal the resources or use them. And that's useful if you don't need those resources anymore. You're not worried about losing information about that thing. You don't need it anymore. You can pass it in as an R value reference. Now, this is kind of annoying to type, so the standard library gives us a nice shorthand, std move. So all that std move is doing is it's converting this to an R value reference. It's casting it, and it does the same thing. Now, all the standard library containers are already wired up to be able to take advantage of move semantics. So let me give you an example. So if I got a string A, and then I want to create a string B that's a copy of that, that'll look like this, and that runs fine. Yeah. Now, what if I want to create B? I want it to have the contents of A, but I don't need A anymore. I don't care about it anymore. Well, I can std move from A into B. Now, if I move from A into B, now A has nothing and B has gotten its contents. So, and there's no magic here. A lot of people, when they first learn about move semantics, they think that move is some kind of amazing function that somehow steals the resources from A and jams them into B. But all that move is it's just casting to our value reference. The mechanics are in the in the members of string here. So B is going to have a constructor that takes an R-value reference, and that constructor will steal the resources from the thing that is passed in. And that constructor, this constructor that takes an R-value reference, is called a move constructor. And there's also an assignment operator that takes an R-value reference to the same type, and that is called move assignment. Now, there's another way that the containers are wired up to use move semantics. So, for example, when a container has to reallocate and grow its memory, and it is copying over from the old block to the new block, what it actually does is it calls std move and converts those to R-value references. So it's going to try to do a move. Now, whether or not it can actually do a move depends on the type that the vector is containing. So if that type has move constructors and move assignment, then it'll work. If not, well, if you pass in an R-value reference and there is no R-value reference copy constructor, it will just default to the normal copy constructor, the normal reference version. So right now, vector is converting to R-value reference, but that is getting dispatched to, I guess it would be this function here, the copy constructor. But what we can do is we can add a move constructor, surface, and then instead of performing the deep copy and then destroying the old buffer, it's just going to give this memory to the new surface. So what we can do in the move constructor here is all we're going to do is we're going to write some code that will pilfer the data from the donor. So it's got to have the same width and the same height. And then we're going to make the pointer point to the same memory that the donor's pointer is pointing to. Now, because we're transferring that ownership, we've got to now make the donor dot p pixels equal to null pointer. It no longer owns that memory. Now the new surface owns it. And there we go. We've pilfered the memory from one object into another. And let's also put an announcement in here. So now it's surface move constructor is called. And if we run this, you see now it's no longer calling the copy constructor, it's calling the move constructor, and it is not allocating new memory anymore, and it is not deleting that old memory. It's just pilfering from the other one. It still calls the destructor from the other guys, but those guys are going to have their memory pilfered. They're going to be pointing to null pointer, and we're not going to have to destroy that memory. Now, if you're going to be doing a move constructor, you should also be doing move assignment in general. So create a move assignment operator here. Basically the same idea as the copy assignment. First, you should be checking, I missed this on the first time when I talked about this stuff, but you should be checking that the thing being moved and the thing being moved to are not the same thing. So if the address of right-hand side is not equal to the address of this object, then we do the copy, well, the move, I should say, which is we copy the width, we copy the height, we delete. If we have something, if we're already owning some memory, we delete that, and then we make our memory point to the memory of the right-hand side thing, and we make the right-hand side thing point to null pointer, and there you go. You've transferred ownership, you have pilfered that resource. Let's fix this one here while we're at it as well. And there you go. That should be the move operations all implemented. One thing I always forget to do is return star this. Got to return that reference to the self object. Let's also add an announcement function while we're at it. And now if we do that, it's going to enable us to move from one surface object into another. Pilfer the resources from this one, put it into this one. And there you go. You see the announcement here at the very end, surface move assignment called. Note that if I did not implement the move assignment operator, this would just default to a copy. So it's not like if you try to move and you don't have a move assignment, you get like an error or anything. It just defaults then to the copy. And there you go. That is how you enable move semantics for your types. You implement move constructor and move assignment. And now I can tell you the full story, because remember when I taught you about rule of 3? Well, it's actually the rule of 5. The 5 special members that are part of the rule of 5. You can see them here on this table. The destructor, copy constructor and assignment, move constructor and assignment. And if you implement any one of these guys, you should probably be implementing all of them. That is the rule of thumb. And this table is actually useful. You can find this on the internet. Just search for rule of 5 in Google image search, and it tells you how when you implement or when you supply or declare some of these, what happens to the other ones, which ones the compiler no longer gives you, which ones are deleted, etc., etc. One thing you should be aware of is the behavior of the default move members, and they're basically the same idea as the default copy members. So if I've got a class here, dog, it has a move constructor that announces, and then I've got a class cat, it embeds a couple of dogs. If I try to move construct a cat from another cat, it is going to move, it's going to try to move the dogs from C1 into the dogs from C2. That's the default behavior. If we run this, we see, yeah, move constructing a dog, move constructing a dog. So from this, what we can understand is that if our classes, like our cat, only has types that know how to handle themselves, know how to handle their resources, like a std string or a std vector or something simple like an int, you don't need to supply any move members, same as you don't need to supply any copy members. The defaults work fine, and that's the rule of 0. The rule of 0 still applies here. So forget about rule of 3, it's now rule of 5 or rule of 0. And I always prefer rule of 0 if you can swing it. Now, while we're back in this code base here, there's something I just want to clear up, and it's these functions here. I would never actually write functions like this. Let me tell you the reason. First off, what we're doing here is we are going to copy the string and then do some work on it. Or in the version down here, if it's an Rvalue, we can just work on it directly. But here's the thing, string, it is all wired up for move semantics. It has all the move operations enabled. So what we can do is we can take string by value. What that means is that if we pass in an L value, it is going to make a copy. And if we pass in an R value, it is going to move that data into this local variable. So we're still going to avoid unnecessary copies if we don't need them. And that's beautiful. So we can get rid of this, get rid of that. This is going to be string, and so is this. And here you go. We've got one function. It does everything we want. All we got to do is pass in by value. So if we pass by value, there we go. If we need a copy, we're going to get a copy. If we need a move, we're going to get a move because string is wired up for move semantics. So if we run that down here, we should get the proper stuff here. Yeah, nom nom nom, we get that, but the after nomming is still the normal string. It hasn't been touched. And then here we get nom nom nom. Now, what if I put a std move in here? Move. So predict what the output is going to be for this. Let's run it. After nomming, it's blank, right? Because we moved those resources from the string s into the temporary of the function. So it's now empty. It's a little different than what we had before when we were just passing an Rvalue reference and working on that string directly. Here we're actually transferring those resources into the local inside of the string. So if we don't need s anymore, we can just transfer its resources right into the function and the function can work on them. But if we do need s, then we pass like this and it will make a copy for us. So this is generally how you would take advantage of that situation. You don't have to write a second overload usually in order to take advantage of move semantics. But if you are writing a class like Surface that has to manually manage its resources, its memory resources, then you are probably going to have to implement all of the operators: copy, move, and destructor. All 5. Rule of 5. All right, now there's one big problem with the surface that we've created now. Before, with our surface, we had the condition that it was always going to own some memory, some grid of pixels. So you either construct it by loading from a file or by creating a surface with a width and a height. You would never have an empty surface, right? But now we have the situation where we can pilfer from a surface. We can have a surface that is empty. So we've got to consider that in our code. Now, the easiest way I can figure doing that is just set the width and height to 0 when you have an empty surface. That way, putPixel is going to fail assertions, and other things you'll be able to see if you have a width or a height that's 0, you'll be able to test whether a surface is empty or not. So in order to do that, all we got to do is we set the width and the height of the donor to 0 here. We'll do the same for the move constructor, and that should actually just about be enough to ensure the class invariant for surface. So now it makes sense. Now since logically we can have surfaces that are empty, might as well add to surface a constructor, a default constructor that will construct an empty surface. It'll be a nice addition. In fact, all we have to do here is set this to default. And then down here, just give these guys defaults of 0 and 0. And that will be enough to have our default constructor. So yeah, one thing to watch out for if you are creating a type and it is able to be pilfered from, you have got to consider the situation where the state where it is now empty. All right, let me show you one last thing with move semantics and then we're done for today. So let's say we've got a vector here of strings, and what I want to do is I want to filter this vector. I want to only keep the strings that have a length greater than 10. So what I'm going to do is I'm going to use std back inserter to insert into a different vector here, and I'm going to copy from this one into this one only if the length is greater than 10. So I can use copy if to do that, and then I'll just output the results here with std copy and ostream iterator. And if we run that, we should get the expected result. Yeah, McChicken sandwich. That's probably not how you spell turrets. Okay, so those are the two strings that have length greater than 10. Now here's the thing. What if my original vector, what if I don't want to keep this afterwards? What if I'm going to be getting rid of it? Wouldn't it be nice if I could run copy if, but actually do a move if? So if it satisfies the condition, move the string resources from inside of this vector into here. Well, we can, and how we do that is we use a little cool little dude called a move iterator. So we do std make underscore move iterator, and there we go. We just turn this guy into a move iterator. Now I believe that the begin and end have to match, so we make this guy also a move iterator. So just clean that up a little bit. So the input iterators are now going to be turned into move iterators, so we can move out of them, and we are going to be moving in with the back inserter into here. And I'm also going to output here the result of what is left in the vector v after we have stolen some strings from it. So if we run this, we can see here McChicken sandwich. That's probably not how you spell turrets. And then here, the two things that got stolen from the original vector. So we got these blank spaces where we moved out of those strings into our other vector. So you can use make move iterator with a lot of the algorithms in the standard library and use that to move your shit instead of copying it, which can be a lot more efficient in certain situations. Very nice. And these move semantics, they're amazing. They're probably one of the most important things that came in with C++ 11 because it gives us finer control over how our resources are managed, and we can reuse resources of things that are going to die anyways, and we can have a very elegant way of being able to move resources from one container into another. And another thing this lets us do is this lets us create types that cannot be copied but that can still be moved, and so we can have non-copyable unique types. You can't make a duplicate of this, but you can still have it in a container and still solve the problem of when the container grows, how you've got to move from one block into the new resized block. And that is going to tie nicely into the next video I'm going to do on smart pointers, because the unique pointer, the most important smart pointer, is a type that is just like that. It cannot be copied, but it can be moved. And move semantics is what enables such a type to exist. That's going to about do it for today. Thanks for watching. I hope you enjoyed the video. If you did, please click the like button. It helps a lot. And I will see you soon with some more C++.